So this is what I was talking about. Mechanics C, 2017, question 1. Our friend the Atwood's machine. So looking over this, over a frictionless pulley, negligible mass, that's important. But I first started Atwood's machine, I'm like, great, this is either forces and torques, but it's not torques because frictionless pulley, thank God, making my life so much easier, or maybe energy depending on what they're asking for. M1 and M2. M2 is always greater than M1. That's super important, so I'm just going to circle that, right? M2 is greater than M1. So on the dots below, which represent the blocks, draw and label the forces, not components. So let's talk about that. So not that there are components in this problem, but the AP exam is just dumb for a very specific reason. They think free body diagrams have importance in and of themselves, and therefore they're purists about them. They require that you never draw components on their free body diagram, even when the problem requires you to resolve the damn forces into components in order to solve. When they give you a dot in order to draw your free body diagram on, don't draw components. Never draw components. Unfortunately, then you're going to have to separately on the side, somewhere not attached to their dumb dot, draw your own free body diagram so you can actually do the problem. It infuriates me that they do this. There's no reason for it. I don't know. It's just the worst type of bureaucracy. Anyway, sorry for that rant. Here we go. No components on free body diagrams. Now, each force must be represented by a distinct arrow on and pointing away from the appropriate dot. The relative lengths should show the relative magnitudes. Now, that's not normal, so but we should just acknowledge that. So here we go. I'm going to draw FG1, and I know that M2 is larger, so let's just draw a bigger arrow there. FG2. Now, what about the forces upwards? Well, here's the thing. I know that mass 1 is going to accelerate upwards. That means that the tension upwards has to be greater than this force so that there's a net force up. At the same point, I know that this is accelerating downwards. That tension's got to be smaller than this. But the way I made it that the tensions are the same as well, so it's got to be bigger than this but smaller than this, so it looks like 2.5. So I'm just going to go 2.5 up on each. Boom. That's not normal that they ask you to do the relative sizes, and if they don't ask you to do relative sizes, you don't worry about it. So there you go. Nice free body diagram. So using the forces in your diagrams, write an equation applying Newton's second law to each block, and use those two equations to derive the magnitude of the acceleration. Now, that's annoying because they said to each block we can't use our system analysis because they've essentially said that we can't, which is dumb, but that's what they want. So I'm going to say up is positive there, down is positive there. We're going to use our bent axis declaration, which, by the way, they hate, but they still will mark right because they're not that terrible. But there we go. That declaration system lets me say that A1 is equal to A2 is equal to A, because we know equal distance and equal time. They don't care about those niceties, even though I think that's actually the most important thing. So here we go. We're always going to start with F net equals MA, and this is for object 1, so there we go. And F net 2 equals M2A2. Now, believe it or not, ready? You don't write F net equals MA, you get 0 credit for this. If you don't have the premise, you don't get any of the credit that goes afterwards. They're very, very particular about that. So here we go. I've got tension minus, and I'm just going to put FG1 equals M1A1, and then this is FG2 minus the tension is equal to M2A2. Now, we've done all our work talking about why is A1 equal to A2 and have done all those discussions. That's just like they're not making a big deal out of it, so neither will we. So all I'm going to do here is solve for the tension in one place and plug it into the other. So T is equal to M1A plus M1G. And so then this is M2G minus M1A plus M1G is equal to M2A2. Now, you'd normally have a lot more space in your exam booklet to do that, but let's just deal with the space I have here. I'll probably go to a little blank sheet of paper here just to make this a little bit easier if I have one. Ah, perfect. Okay. I'm not sure. They might just say do this on blank paper. I'm not sure what it's going to look like. But this is the expression that I care about now. So here we go. M2G minus M1A minus M1G equals M2A2, or A, just A, right? And so then M2 minus M1G is equal to M1 A plus M2A, and just divide it across, so now we have our expression. That's equal to M2 minus M1 over M1 plus M2, quantity G, and we've got that done. Yay, we got the same expression. So a verify type problem. Okay, great. So now let's get down to brass tacks. This is where the fun begins. So typical. This is so typical of the type of problem that they ask. So they give you a bunch of data, and here they gave us M1s and M2s, and given an M1 and M2, this is what A is. And what they want is indicate below which quantity should be graphed to yield a straight line whose slope could be used to calculate a numerical value for the acceleration due to gravity. So here is the skill, folks. We'll come back to this particular one in a second, but let's say we have a falling object, right? So y is equal to y initial plus VIYT plus 1/2 AYT squared. And we know that AY here is G, and we want to find out a value for little g. Let's say they give you y values and t values. What would I graph? Well, here's what we would graph. Let's say we know that that and that are 0, so we know that y is equal to 1/2 gt squared. So the first part of this problem is always find some sort of link between the variables that you have data for. Then, in order to know what to plot, remember what we're trying to do is get a straight line. Always that's going to be the goal, is a straight line. So we're linearizing this function. So think y equals mx plus b. Well, here there's no plus b term, so no worries. So I can look at this and say, oh, well, if my y values are my y values, I want the slope to be g, which is what I'm looking for. That means x has to equal 1/2 t squared. So what I'm going to do here is I'm going to make a new column that is 1/2 t squared, and then when I plot it, that y and 1/2 t squared, that the slope of this line equals g. That's the way we do this. We make the equation that links the data that I know. I look at the format of the equation, and then I transform the data in order to make it work. So here, they're looking for an expression for little g. But remember, what's my expression here? I've got a is equal to m2 minus m1 over m1 plus m2 little g. I want to make g my slope. Oh, okay, so if on the vertical axis, I could plot, if you think y equals mx plus b, I want this to be my m, I can make, on the vertical axis, plot the acceleration. And if I plot the acceleration in the vertical, and if I plot m2 minus m1 over m1 plus m2 on the horizontal, I've got it. Another way, alternate, you could do a times m1 plus m2, and then on the x-axis, just do m2 minus m1. Whatever it is, either of those would give a slope of g. Got it? And so here we do. I'm just going to do this. So they gave me some other rows. I'm just going to say my last row is just going to be m2 minus m1 over m1 plus m2. So that's 2 minus 1 over 3, so 0.33. And this is going to be in kg. Just make sure, oh, actually, no, this has no units, right? No units. And then 3 minus 1, so that's 1 over 5, 0.2. Now I've got 7, woof. See, this is just where they start getting nasty on you, if that's what you choose. I've got 7 divided by 17. 7 divided by 17. I'm just going to go 0.41. Then I've got 8. So 2 divided by 14. 2 divided by 14 is 0.14. And then I've got 4 divided by 24, 0.17. Oof. So looking at that, that's my horizontal axis. Now I have to look at my values, and it looks like I'm ranging from about 0 to about 5. So this is going to be 0.1, 0.2, 0.3, 0.4, 0.5, and I'm going to label this M2 minus M1 over M1 plus M2. So this is just really time consuming, you can see, right? A in meters per second squared. That's why this first problem they're going to give you 25 minutes for, because there's just a lot of stupid manipulation to do. Looking at my values, they go between 0 and 5. Oh, conveniently 1, 2, 3, 4, 5, haha, right? So you can kind of see that they give you a little bit of a hint as to what you should be doing here. Because if you get something that won't fit nice, then it won't work. So let's see, clearly scale and label all axes, including units if appropriate. Nice hint there. So that's that. And I'm even just going to write no units here because I don't want to even get into it, have anyone guess. So now I'm just going to plot my data. So it looks like the first one here is this one, 0.14, and the A here is a little less than there. Okay. Next is the 0.17. So 0.17 is going to be between these two jabronis, and that is up about there. And then 0.2 and 1.8. Okay. Well, that point's terrible. Let me just make sure I calculated that right. 4 divided by 24. Yeah, okay. Next, 0.33, so that's here. That's 3.0. Yes, okay. So clearly there, it's data, so there's going to be outliers and whatnot. They're going to see that, do you connect the dots, or do you know what a best fit line is? So hopefully you know not to connect the dots. 0.411, 42. Boom. And so here we go. I take my straight edge, and I'm going to, I'm not going to obsess about 0, 0 here, and I'm just going to make a best fit line. And all you have to do is make a defensible best fit line. It doesn't have to be amazing. That's actually not great, to tell you the truth. I probably should have pushed that upwards, but it doesn't matter. So using your straight line to determine the experimental value for G, here I'm just going to say G equals slope. Now, that's not always true with slopes with this. Sometimes you plot things and what you're finding is areas, right? For example, a velocity versus time graph, the area is the displacement. A force versus position graph, the area is the work. A force versus time graph, the area is the impulse. You always want to have a statement about, like, what about your graph? The slope equals this, right? The area equals that. Something about your graph that lets us know what's going on, what your premise is. Now, here's where they just get absolutely mental, right? You have to show a plugin for something minus something, something minus something with the right units. You miss any of it, no credit. Even worse, you gotta pick points that are on your best fit line. If you pick points that are off your best fit line, that are your data points, you get no credit. So I'm gonna come here and pick 2 nice points, right? So that one's nice because it intersects there. And this one's kind of nice because it actually goes through my data point. So I'm going to pick those 2 points. So I've got 2.4 meters per second squared. And this is at 0.26 nothing. And then this one is at, that's the data point for this one. So it is minus 1.15 meters per second squared. And then this is minus 0.14, but 0.14, right? So there we go. Let's plug that in. 2.4 minus 1.15, right? 1.25 divided by, and this is 0.12. Let's plug that into our calculator, and we get a value of 10.4 meters per second squared. And the problem continues. The experiment is now repeated with modification. Oh my God, these problems are so long. The Atwood's machine is now set up such that the block of mass M1 is on smooth, no friction, M2 is hanging over the edge. For the same values of M1 and M2, is the magnitude of the tension in the string when the block's moving higher or lower equal to the magnitude of the tension before? So what do we think about that? Well, the justification, they don't say that I can't use something about, I can't use, excuse me, equations. So here's the thing, what I would do in this case is, I would say to myself, well, I know from the previous problem that the free body diagram for that is staying the same. So therefore, I know that Fg minus T is equal to ma, so Fg2, right? So the question here is, what happens to the acceleration in this case? Well, the acceleration here is actually, rather than if we look before in the way that we derive this, the net force for this system is going to be larger. Because if we think about it in terms of our system analysis, before when we had the Atwood's machine, we had a gravity force pulling down and a gravity force pulling down, and this was the subtraction of those two gravity forces that was the net force. And I would say here that the acceleration of this system is larger than Atwood, because the net force is Fg2 rather than Fg2 minus Fg1. Okay, so therefore, if I look at this, then T is equal to Fg2 minus Ma2 if A2 is larger, therefore T is less. And notice I'm referencing an equation, right? I'm not really solving for things, but I'm using equations as my as my way of figuring out my justification. Even if they say don't solve for things, that doesn't mean that you can't use equations. Are just mathematical representation of the logic of causality. So even if you don't solve it, citing equations and then talking about their proportionalities is total valid game. The value determined for the acceleration is lower. Give one physical factor that could, okay, well, simple here. They made our lives easier. What could make G lower? Oh, we didn't account for air resistance. It's such a terrible, terrible answer, but it fits it, right? And we would say there, F air reduces net force, therefore reduces A, right? That would be one thing that would account for that. Another thing that could account for that, like, oh, it doesn't say right, oh,